right, this leads us to the second type of transformation, which are called dilations. It depends on what textbook you use. This particular book doesn't call them dilations, it calls it shrinking and stretching. I liken it to looking at like a mirror at a carnival. You either get real short and real wide, or sometimes you get real tall and real thin. It kind of reminds you of that. It's going to be what we call a non-rigid transformation. Translations, or shifting, was a rigid transformation because the shape did not change. But in this case, the shape is going to change. It's either going to get stretched or shrunk. So there are two types, of course, vertical and horizontal. We're going to look at vertical first. And it says, consider a function defined by y equals f of x, and let a, I underlined a here, represent a positive real number. So a is a positive number. If a is greater than 1, then the graph of, notice where the a is, it's times the function this time. A times f of x is the graph of y equals f of x stretched vertically by a factor of a. I mean, think about it. You plug in a number here, you get f of x, maybe it's 5. And then if a is greater than 1, let's say it's 2, 2 times 5, all of a sudden it doubled. So it's stretched vertically by a factor of a, whatever a might be. Now if a is between 0 and 1, still positive, then the graph of y equals a of x is the graph of f of x kind of squished down, shrunk vertically by a factor of a. Now of course if a equals 1, 1 times f of x is going to be f of x. It doesn't change the graph at all. So I set up a t-chart, or actually kind of like a triple t-chart here, because I want to graph the following functions. I'm going to graph the first two here. F of x is equal to x squared. That's your parent graph. So if I plug these values into x squared, I get 4, 1, 0, 1, and 4. And I can graph those points. And come up with a hopefully reasonable sketch. 1, 2, 3, 4. If I can count to 4, I can get a reasonable sketch. And I get my basic parent function, quadratic function, parabola. Now, if I do this for g of x, which is 3x squared, notice the 3 here is going to stretch it. So if you can picture this graph, the x-intercept is not going to change because the y value is 0, and 0 times any number is going to stay 0. But it's going to get stretched like a mirror at a carnival. You're going to look thinner, skinnier, and taller. So what happens here, and I'll use green for this one, if I plug negative 2 into here, negative 2 squared is 4 times 3 is 12. Negative 1, let's see, into here would be 3, 0 would be 0, then 3, and then 12. Might have to make this graph a little bit taller. How far did I go up? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm going to go all the way up into my writing. And that way I can graph these two values here. So I'm going to graph negative 2, 12 way up here. Negative 1, 3, 0, 0, like I said, same x-intercept, 1, 3, and 2, 12 way up here. This is going to be really tough for me to freehand, and I better do this in green so you can see it. But it's going to be a much skinnier, skinnier parabola, U-shape. Definitely you want to use graph paper here and take your time and draw it neatly. As you can see, mine looks a little, well, not so great. It doesn't look exact, but you get the basic idea of the shape. Alright, now, this third one here is h of x is equal to 1/3 x squared. Now the 1/3 in front means that it's going to be shrunken vertically. So it's going to get shorter and wider. So if I graph, now I'm looking off of this here. So let's do this one in brown here. So let's plug negative 2 in. That would be 4 times 1/3 is 4/3. Plug negative 1 in. I get 1/3, 0, 1/3, 4/3. You have to like symmetric graphs. So negative 2, 4/3 would be about here. 1/3 would be about here. 0, 0, 1/3, and 4/3. You can see how this one has been shrunk down, and you get a much wider looking graph. And so on. Now if I had this drawn out a little bit further, I could graph a few more points. Now the last one that I have here, that's circled in red, it's circled in red for a reason. Anytime you see one that's circled in red in any of these videos, it's a problem that came off of the review sheet for the semester exam. So this one I'm going to do, even though it's not a dilation, it's a translation, it's actually 2. Because it's the quadratic and we're doing the quadratic function here, I'm just going to add this one right on here. Now, this is 4 to the right, this is 3 down. I'm going to have to extend my graph here. So 4 to the right, 3 down. If I put these values in here, I'm going to get something that's going to give me some wild values here because it's been shifted. What I'm going to do instead is I'm going to just use the parent graph in black here, shifted 4 to the right and 3 down. So for example, this point here is at -2, 4, 4 to the right, 3 down, that would be +2, 1. +2, 1. Whoop, a little bit below that actually, right about here. There we go. Then -1, 1, that would be at 3, -2. 3, 1, 2, 3, -2. A little sloppy here at the bottom. Hopefully you can still see this okay. 0, 0 would be at 4, -3. That'd be way down here. That'd be the vertex. And then 1, 1 would be at 5, -2. And then 2, 4 here would be at 6, 1. And even though that's kind of a hard graph to follow there at the bottom, you can see it's this shape just been shifted vertically and horizontally in the same problem. Okay, again, anytime you see something that's got a red circle like that, that's a clue that you're going to find that one on the semester exam review, which means it could be similar to something you might find on the semester exam. Alright, now, horizontal shrinking and stretching. I didn't set up a double T chart or a triple T chart or anything like that. I'm going to kind of go through this one because I'm not using a parent graph that's one of the basic graphs. I'm using a graph that's right over here, and that point, that's a point, not an arrow. Okay. It's kind of a V-looking shape there. It says, consider a function defined by y equals f of x and let a be a positive real number. If a is greater than 1, the graph of, now notice where the a is. It's not out in front times the y value times the f of x, it's times the x. Is the graph of f of x shrunk horizontally by a factor of 1 over a? Now you would think if a is greater than 1, you wouldn't shrink it, you would stretch it like you did over here. But it's just the opposite inside the parentheses, just kind of the opposite of what you would expect. If a is between 0 and 1, then the graph of y equals f of x, f of a of x, a times x, excuse me, y equals f of ax is the graph of y equals f of x stretched horizontally by a factor of 1 over a. So if this is like a half or a third, that's where you get the stretching horizontally, stretching out. Now it says the graph of f of x is shown. That's this one here. I'm going to graph these two. And I picked two fairly simple ideas, multiplying by 2, multiplying by a half. Now, if I'm multiplying by 2, according to this, it's going to shrink it. It's going to make this v a little bit more narrow than before. So what I'm going to do here is I'm going to use the 3 key points, here, here, and here. This is 1. If I plug 1 into the original function, f of x, I get 2. Well, for this guy, I'd have to plug in a half, because 2 times a half would give me 1, and f of 1 is 2. So I have a half 2. Right there it is. This point here is at -1, -2. So I'd have to plug negative a half in here to get the -1 that would give me -2. So it's right about here. And then this point here is at -2, 3. I would have to plug in -1 to get f of 2, which would give me 3. So at -1, I'm at 3. And you can see, although I'm going to freehand it, and it's going to ruin the effect most likely, that it is the same V. It's just that it's been squeezed in. It's been shrunken horizontally. That's this guy right here. Now, just kind of the reverse with y equals f of 1/2 x, I'm going to plug in values that are going to give me these key numbers of 1, -1, and 2. But to do that, since I'm multiplying by half, I'm going to have to take double the size. That's going to stretch it out this way. So to get a 1 here, I'm going to have to plug in a 2. 2 times a half is 1, f of 1 is 2. So I'm at 2, 2. All right, here to get the -1, I'm going to have to plug in -2, and that's going to give me the -2 there. So at -2, -2. Now to get 2, and then which will give me the 3, to get a 2 here, I'm going to have to plug in, a -2, I'm going to have to plug in -4. So 1, 2, 3, 4, and that'll get me up here to 3. And now I hope my graph isn't so crowded. And even though I kind of freehanded it here, I don't know if you could really tell because I freehanded it, it's going to have not the same x-intercept, it's going to have the same y-intercept when you do horizontal shrinking and stretching.